The universe undoubtedly expanded, stretching endlessly for an extended period. Over time, this expansion slowed down, eventually transforming into the universe we observe today. This theory, known as the inflationary model, is the most widely accepted explanation for the universe's origin. However, some physicists argue that this theory doesn't fully explain the creation of our universe. They propose that the universe may have existed before the Big Bang, stretching infinitely into both the past and the future. In this view, the Big Bang wasn't a singular event but rather a transition, like a leap, a second one in an ongoing process of expansion and contraction, possibly repeating itself in cycles. Some theorists suggest that the universe could be eternal, with no clear beginning or end, continually undergoing expansions and contractions. Brian Cox, a prominent physicist, challenges the traditional view of the Big Bang, pointing out that something cannot emerge from nothing. This adds to the growing tension surrounding the idea of the Big Bang being the universe's origin. The James Webb Telescope has uncovered discoveries that challenge the Big Bang theory, leading to the question: if the Big Bang wasn't the start of the universe, then what was? Could the universe have always existed, or perhaps originated from something entirely different? The concept of a universe with a definitive beginning dates back to Georges Lemaitre in 1927. While the idea that the universe had a start is widely accepted, some argue that it has little to do with the Big Bang itself. There is a growing body of evidence suggesting a more complex, less specific origin for the universe, one that challenges the standard cosmological model. The universe we observe today, defined by inflation, began well before the Big Bang. This early stage was an empty void, devoid of matter or radiation, where space itself was filled with an immense amount of energy. Over time, this energy transformed into matter and radiation as the universe cooled and expanded, eventually leading to the creation of the universe as we know it. This process is marked by a rapid transition from pure energy to matter, with the temperature initially rising and then cooling down. The universe's expansion continued at an accelerating rate, slowing down only later in its history. The cosmic microwave background, CMB, carries the imprint of this early expansion, providing crucial evidence for the Big Bang. However, there are still unresolved anomalies within the CMB, suggesting that our understanding of the universe's early stages may need revision. In this expanding universe, as regions stretch farther apart, the speed of this expansion decreases. The distance between objects in space doubles over a set period, and this process continues indefinitely. However, as the universe moves from one stage to another, regions of space that were once connected become increasingly isolated. These regions, which are increasingly influenced by radiation and antimatter, will eventually become more distant from each other, making it less likely that any separate universes will ever interact. As the universe continues to expand, the forces that govern space itself change, leading to regions with more uniform particle distributions. Over time, quantum fluctuations or instabilities create slight variations in density across the universe, forming the seeds of large-scale structures. These density instabilities can be observed in the CMB, providing a snapshot of the early universe's conditions. The details of these fluctuations are crucial to understanding how the universe evolved from the Big Bang to the complex structures we observe today. Despite the evidence for the Big Bang's role in the universe's evolution, the precise nature of its origin remains uncertain, with some scientists proposing alternative theories that could better explain the universe's inception and evolution. In modern cosmology, there are several intriguing anomalies that suggest we may be missing something crucial in our understanding of the universe. These anomalies can be summarized in 4 key areas. First, at extremely large scales, the universe does not behave as expected. The cosmic microwave background, CMB, light is being lensed through structures in our universe, causing it to act like a giant magnifying lens. This bending effect alters the intensity of the CMB in ways that are inconsistent with current models of cosmology. Second, there are temperature fluctuations across the CMB sky that contradict the assumption of consistency in the early universe. These variations challenge the idea that the universe began in a perfectly uniform state, as current models suggest. Third, there is a discrepancy in the measurement of the Hubble constant, which describes how fast the universe is expanding. depending on whether we measure it using the CMB or nearby stars, the rate of expansion varies, indicating that our current models may be incomplete. Finally, these anomalies suggest we are missing something fundamental in how we interpret the universe. One proposed solution comes from loop quantum cosmology, which stems from loop quantum gravity. In this framework, there is a smallest possible scale, or quantum size, for spacetime, approximately 1.0 x 10⁻⁻35 meters. According to this theory, the Big Bang may not have been the origin of the universe, but rather a transition from a contracting universe that later expanded again, similar to a phoenix rising from the ashes. While the idea of a cyclical universe is not new, loop quantum cosmology offers a mathematical structure to support this notion. If loop quantum cosmology is correct, it could explain some of the anomalies we observe, such as the temperature fluctuations in the CMB and the lensing effect. This approach suggests that the early universe may have had low energy and density, which could have affected the CMB and led to subtle variations in temperature across the sky. Additionally, this model provides a potential explanation for the Hubble constant anomaly, proposing that quantum gravity effects might explain the discrepancies in expansion measurements. By integrating quantum mechanics with general relativity, loop quantum cosmology offers a promising avenue for addressing some of the long-standing mysteries in cosmology. However, questions remain. Some physicists argue that the concept of an eternal universe, as suggested by cyclic cosmology, encounters a significant problem: entropy. As entropy increases with each cycle, it would eventually lead to a state of maximum disorder, contradicting the idea of an ever-renewing universe. This dilemma challenges the idea of a timeless cosmos and suggests that the universe must have had a definitive beginning. Cosmic observations, particularly the acceleration of the universe's expansion during the inflationary period, have led to a more nuanced view of the Big Bang. Instead of being a singular event, the Big Bang is seen as part of an ongoing process, with the universe expanding from a highly energetic state. The transition from this energy into matter marked the end of inflation and the start of the hot Big Bang. Some physicists propose that the universe may have existed before the Big Bang, perhaps undergoing a contraction phase. This challenges the traditional notion of a single starting point and introduces the idea of a cyclic or eternal universe, where cycles of expansion and contraction repeat endlessly. This theory, which combines elements of cyclic cosmology and quantum mechanics, posits that the current universe is just one iteration in a series of cosmic cycles. Recent cosmic observations, such as fluctuations in the CMB and the distribution of galaxies, have raised questions about the simplicity of the Big Bang model. These anomalies suggest that our understanding of the universe's origins may need to be revised. The development of alternative theories like loop quantum cosmology, which attempts to merge quantum mechanics with general relativity, offers new insights into the universe's earliest moments. In conclusion, while the Big Bang theory remains the dominant explanation for the universe's origins, ongoing research and observations continue to challenge and refine our understanding. New theories, such as loop quantum cosmology, provide promising solutions to some of the anomalies we encounter, and they may eventually lead to a more comprehensive framework that addresses the complexities of cosmic evolution. The question of whether the universe had a definitive start or has existed eternally remains a central issue in cosmology, driving further exploration and discovery.